Why does fluorine have a low van der Waals interaction energy and iodine have a large van der Waals interaction energy? Are there any ion dipole, dipole, any ionic bonds here? Nope, they're all symmetric molecules, no dipole stuff going on, none of that. And so why does this one have a large interaction energy and this one has a small interaction energy? It's more polarizable. Remember, there's more electrons in iodine. More electrons. What else is iodine compared to fluorine? What's special about fluorine? Very electronegative, right? So this one holds on to its electrons tightly, and there aren't many of them, and so this has low polarizability. And this one has high polarizability. Which one's got the higher dispersion forces between them? Iodine, right? So London dispersion forces, van der Waals interactions are all the same thing. And so when you're just dealing with nonpolar molecules, you want to look for polarizability. And that determines the strength of the interaction between these molecules. Yeah?
So radius, atomic radius has a key here too, right? Because it's going to be bigger in the bottom of that list.
So
have easier time stripping electrons from further away from the nucleus.
Yeah. So this has more electrons, and it's basically more to polarize, right? So it's more polarizable. So it's not necessarily that the radii are bigger, because that doesn't hold for the gases, right? Because the molecules are so far apart. This is not a 1 over r to the 6, you know. I think there's one, let's see, where is that formula? Let's just take a look at that. Here, so you have these van der Waals forces where they scale with 1 over r to the 6th. And so the size, this basically is the force between one fluorine molecule and the other fluorine molecule. As you bring them together or bring them apart, the force, or the van der Waals force between these, varies with this 1 over 6 relationship. But this is not the size of the atom. The size of the atom really relates to how many electrons there are. So if I ask you, how does the force vary between two molecules as I move them closer together or further apart? That's a 1 over r to the 6th type relationship. So it's not, say I could ask you if two molecules are 3 nanometers apart versus two molecules are 10 nanometers apart, does the force vary by 3 over 10? And you would say no, it varies by some larger factor than that. But the size comes into play when you're talking about the electrons, because this is what's polarizable. Right? When we're talking about interactions between molecules, we're really talking about electrons and how those electrons are moving. So that's the important part to that problem. And there were lots of people who didn't understand number 9 from the first exam. So if you get this polarizability part, that'll be an important component for the final, I think. So remember what those key questions were in exam number 1. Next question. Other questions? Does everyone remember exam number 1? Yeah, a little bit? A little foggy? Here, let me see exam 1. Let me tell you what the other key question is on that one. I remember thermodynamics. I remember the other stuff. Oh, okay, so question number 7. Circle the material with the higher refractive index. Which material's got the higher refractive index?
The second one, on the right.
Why?
It was an answer.
More polarizable, yeah. More polarizable, right? Refractive index, dielectric constant. The question is always more polarizable. Number 8, explain why dispersive interactions can be used to explain the behavior of a material such as hexane or benzene, but dispersive interactions are not useful in fully explaining the properties of water. Why is that? Water has hydrogen bonding, and there's no hydrogen bonding in nonpolar molecules. We already did 9. Ideal gas law, you should get this. Number 2, you should get that. Molecules in order of their boiling point. Sodium chloride has a molecular mass of 58, while bromine has a molecular mass of 159. So bromine is bigger, or heavier at least. Why is sodium chloride a solid at room temperature and bromine a liquid at the same temperature? Ionic bonds, right? Ionic bonds are very strong. That causes you to have a solid. What interactions are in bromine? Dispersion, van der Waals interactions. Good. Van der Waals interactions occur only for nonpolar molecules. True or false? False. Under what circumstances do you have van der Waals interactions? All the time, yeah. So van der Waals interactions occur no matter what's going on. And then you have hydrogen bonding on top of that, ionic interactions, etc. Dipole moment, you can look that up. 3 types of van der Waals interactions, you can look that up. Spectroscopy, you just need to study that. Circle the situation where the strongest forces exist between Na plus and Cl minus ions. Sodium chloride in vacuum or sodium chloride in water? Why?
What was the question?
So what situation gives you the strongest force between sodium cations and chloride anions? Sodium chloride in vacuum or sodium chloride in water? When do you have the strongest force between that sodium and that chloride?
In vacuum?
In vacuum, why?
Because in water, I guess it's like dissolves something.
Yeah, what's the difference between water and vacuum? Water has a high what? Dielectric constant. And so we know that it's in this somewhere. Where is it? Oh. That's not explicitly in there. But anyway, so solubility. So you get solubility of NaCl in high dielectric constant solvents, right? So is sodium chloride more soluble in hexane or more soluble in water?
Water.
Yeah, It's more soluble in water because water has a high dielectric constant and hexane has a low dielectric constant. Let me, oh, it's right there. There we go. Yeah. So the solubility or the mole fraction that's soluble is proportional to 1 over the dielectric constant. So this formula doesn't necessarily matter for your final because you're not going to have to plug stuff in. However, I could ask you about how the solubility varies with dielectric constant. So you remember this plot where you have solubility and you have 1 over dielectric constant down here. Where's the high dielectric constant part of this graph? If 1 over dielectric constant is plotted here. High dielectric constants are right here, right? And so you have high solubility, and then the solubility drops as the dielectric constant drops. So that's the important part of question 12 on exam 1. Let's see, percent ionic character, that's not going to be so important. So question number 14, explain why sodium sulfate is more soluble in water than in butanol. So that's exactly the same question, right? Sodium sulfate is what type of compound? Ionic, so there are ionic bonds between the sodium and the sulfate. And so butanol is polar, but it's not as polar as water is. Water has a higher dielectric constant. Then you have delta G equals delta H minus T delta S. Hopefully you know how to use that equation. Approximate oscillation frequency of induced dipoles. How fast do induced dipoles move in molecules? How fast do electrons move? 10 to the 15th what? Orbits per? Yes. Cycles per second. A frequency 10 to the 15 hertz. You know, lots of people gave me something without units. So remember, when I ask you for a quantitative number, remember to